Alright, is everybody ready? Sorted? As good as it's going to get? Alright, so today we are going to finish this chapter on boiling point and freezing points. We're going to finish chapter, whatever this is, 12. We're going to start kinetics, my favorite chapter of the whole book, until we get to acids bases, which is my other favorite chapter, until we get to electrochemistry, which is by far my favorite chapter. This is at the bottom of the list. Alright, so like you guys are doing in lab this week, freezing point, depression, boiling point, elevation, we're just going to kind of hit the highlights of it and give you enough background so you can do the labs this week. Alright, so where we left off, we did mole fractions and we did vapor pressure, how it gets changed depending on the mole fraction. So if you had pure water and you add salt to it, the vapor pressure changes. We're then going to extrapolate that and talk about how, by changing the vapor pressure, we're going to change the boiling point and the freezing point. So let's say I have a solution that is 0.2 moles of sugar in 100 grams of benzene, and the normal vapor pressure of pure benzene is 400 millimeters of mercury. I want to figure out the new vapor pressure of this solution. Right, so using the equation we had last Friday. Right, so they gave us this. This is the original vapor pressure of pure benzene. The big circle up here means pure. I want to find the new vapor pressure of benzene, which means I have to figure out the mole fraction was 1, right? It was all benzene. The mole fraction is going to change, so I have to figure out what my new mole fraction is going to be and then calculate my new vapor pressure. So, mole fraction, alright, this over here. Obviously it's a fraction. What kind of number do I need to put on the top for this? Moles of benzene. Did I give you moles of benzene? I just gave you grams. Alright, so how do I get from 100 grams of benzene? What piece of information would you need to look up or calculate? Molar mass. And it happens to be that the molar weight of benzene is 78.1 grams per mole. Everybody should be double checking with their math today. I actually didn't look at my notes before I walked in here, so good chance you're going to mess something up. We got 1.28. Okay, so that goes on top. What goes on my denominator of my mole fraction then? Total moles. So it's going to be 1.28 plus the 0.2. So the mole fraction of benzene is now right to 5. Alright, so now we're ready to plug it back in. So my new vapor pressure is 346. So what happens to my vapor pressure compared to the original vapor pressure? Right? It went down. So we saw a decrease in vapor pressure when we changed the mole fraction, like we added some salt to it. So this leads us to be able to extrapolate to talk about how this change in vapor pressure affects our boiling point. Does everybody have all this slotted up? Graphs. Love graphs. Alright. So this vapor pressure change causes a lowering of the boiling point. Well, lowering the vapor pressure causes an elevation in the boiling point. So if I look at my graph, right, this is the exact same question up here. I had benzene. I'm going to add some sort of sugar to it. This is the pure benzene curve. Here in, I guess, greenish. This is pure. And then this is when I add sugar to it. Alright, so we just did this point right here. I was at pure at 400, and by adding the sugar to it, it decreased it. So now the new vapor pressure was 346 right here. So I saw a decrease in the vapor pressure. If I take that out to boiling, right, so now, right, room atmosphere is 760 millimeters of mercury. My original point on the line, boiling point is 80. At the same atmospheres, my curve has been shifted, and so I have a new boiling point of 88. So by this curve, you can think about it as shifting kind of down and out. Right? So the vapor pressure is down, but then the curve is farther out here to the right. So that's a boiling point elevation. I was at 80, and now I'm at 88. So pure benzene at 80, a mixture at 88. So you may be thinking, that'd be great if I had a graph all the time. Which, honestly, you should always have a graph on you, just in case. But maybe it might be easier if we wanted to calculate it using an equation. So here is our general equation for how to solve for boiling point elevations, which I think is the exact same equation they have in your lab manual for this week. Alright, so here we have delta T, lowercase boiling point, is going to be our change in temperature used in degrees Celsius. We have this constant K. Which is called the molal boiling point elevation, and it is a known number. And that's in degrees Celsius per molal. Then you have, I think in your textbook they use solute as the lower, it could be solution, solute, either way, the molality of your solution overall. And then I is the tricky thing. It's this thing called the Banff factor, which is a really snazzy name. That just tells us about what kind of thing is being dissolved. So, there's going to be two different I's. You're going to have an I if it's a non-electrolyte, or I if it's an ion. So let's say my non-electrolyte is methane, CH4. Is CH4 a molecular compound or an ionic compound? Molecular compound. So when I put CH4 in the water, should it break into individual pieces? No. So how many pieces is it going to stay in? 1. So I is 1. How many pieces is it going to break into? If it's not going to break into any pieces, then it must be 1. But what if I had sodium chloride? Is that a molecular compound or an ionic compound? Should be ionic, right? Because we already did molecular. This is our ionic compound. How many pieces does sodium chloride break up into when it hits the water? 2. So its I would be 2. It's saying molality is really double. Like if I put in 2 molal of NaCl, it's really 2 molal Na, 2 molal Cl. I need to double how many ions are in solution. So let's go ahead and try it out. Let's say I have this reaction. I have regular water, right, that has a melting point of 0 degrees Celsius at 1 atmosphere. And I put 12.15 grams of zinc sulfate into 161.2 grams of water. In the end, I want to figure out what the new melting point is, but I need to figure out how to go about solving for it. So, I'm looking for this delta T. Alright, this is delta T. That's what I'm looking for. But first, in order to solve it, K is going to be given. I'll give it to you now. I'll give it to you later. K. Alright, so K has to be given to you. First thing we have to figure out is what the molality of the solution is in order to solve this. So, what are the units of molality? Moles of solute over kilograms of solvent. So, we need to find how many moles of the zinc sulfate we have. We need to figure out how many kilograms of water we have. So if I want to figure out moles of the zinc sulfate, how do I use the information given? Yep. Alright, so let's see how many moles that is, I think. 12.5. Alright, so now I have the top part. What factor do I need to use to convert grams of water to kilograms? Divide by 1,000, right? That's 1,000 grams for 1 kilogram. So if I have I'd have 1.1612 kilograms. Alright, so now we're ready to plug in and find the molality. Alright, so now we have everything we need in order to plug into our new equation, right? Delta T equals K and I. Alright, so I'm looking for delta T. I gave you the K. We just found M. I. Alright, zinc sulfate. What do we know about sulfate, SO4? It's an ion, right? So if it's zinc sulfate, that should be an ionic compound. So how many pieces should it break up into? 2. we're going to put 2 in there. Alright, so my change in temperature is this negative 1.74 degrees Celsius. So the question was, originally, what is the new melting point? So the melting point was 0. My change in temperature is negative 1.74. So what temperature will this solution now melt at? It's easy when we're talking about water and it starts at 0. So, was this an example of boiling point elevation or freezing point depression? If I was talking about melting point. Freezing point, right? This is a freezing point depression example. But you use the same equation as if you did a boiling point elevation. It's just saying, based on your new molality, how much will the temperature change in one direction or the other? So in this case, I did freezing point depression. Where the freezing point of a solution is lower than that of a pure solvent. The same general equation. The M is molality, K is going to be given, and an I just depends on if it's an ion or a molecular solid. So, on days that are chilly, like they're going to be for the next few days, right, one of the things that hopefully you keep up with is putting your antifreeze in your car, right, in your windshield wiper fluids, all those things. So the question is, what is the antifreeze doing, besides what the name implies? Preventing freezing, right? So, antifreeze is otherwise known as ethylene glycol. So, water, which was the pure solvent, when you add ethylene glycol to it, you're going to elevate the boiling point, depress the freezing point, and in fact, a water-ethylene glycol mixture, as is in your car, this water-ethylene glycol solution. Alright, water normally boils at 100 degrees. This combination boils closer to 109 degrees Celsius. So you'd have to get your car's innards to 109, so it raises it by 9 degrees. And then, why it's a better antifreeze than it really is a coolant, like you want to use ethylene glycol as your coolant. But the freezing point is now negative 34 degrees Celsius. So it has to be greater than minus 34 outside for your car's antifreeze to freeze. So, luckily you guys live in Georgia and that's not usually an issue. There's some parts of the world where that wouldn't make a difference. Alright, questions about any of that? Alright then, let's move on to some exciting stuff. Hopefully you guys are mentally prepared for the amazingness that's about to happen. Alright, rates of reactions. reaction rates, I guess, interchangeably. We are going to be concerned this semester a lot with determining the rate at which a reaction will proceed. So chemical kinetics is the area of science, chemistry, where we're going to look at over what time period does a reaction occur, what are some things we can do to speed it up, what are some things we can do to slow it down, and then how can we influence it to do a bunch of other things. So, right, rate is a way of talking about how fast a quantity changes with time. So you can think about how fast the size of an apple grows over time. You can think about how tall someone grows over their lifespan, things like that, how something changes given some amount of time. Looking at reaction rates, this is going to be more specifically how fast a reactant is consumed. So if I'm looking at combustion, right, I have gas and oxygen. How fast is the gas being used up? Or we could look at the other side of the reaction. And we could look at how fast a product is being made. Still analyze everything in there. There we go. Alright, so to be able to answer these questions, we have to be able to develop a series of related equations that show change in quantity for some change in time. Alright, so mathematically I'm talking about change in something over change in time. Alright, so your height versus your lifespan. Alright, that would be a change. Change over change. So, change over change, you should be thinking, change, big triangle. Right? Big delta. Since we're looking for the change in quantity over time elapsed, which is big changes, alright, so I could say it like this. Change in x over x is over some sort of change in time. When I'm talking about the big delta triangles, am I saying initial minus final or final minus initial? Final minus initial, right? So I want to know how much of x I had at the end minus how much I had at the beginning. And I'm looking at that change in time, right? How much time has elapsed? So the final time minus the initial time. So, if I wanted to, I want to draw a graph. Who doesn't love a good graph? By the end of the semester, you'll be thinking that too, because we do a lot of graphing in here. So, by the end, you'll be confident in your graphing skills. I just sat in an econ class, just because, and I haven't had econ since I was a sophomore in high school. Good to be a refresher. But they do a lot of graphs. Lots and lots of graphs. So I was like, yay, graphing. So I tried not to cheer from the back row. Graphs, graphs, graphs. Because that might have been distracting. But in here, feel free that next time we get to a graph, wildly excited next time you're ready. Because there's going to be a lot of graphs. Alright, so let's say I want to mathematically graph what I just stated over here. So I'm going to put time on the x, and concentration on the Y. If you have multicolored, this would be an excellent time to do some multicolored stuff. I know lots of people have lots of different colored pens. Some people don't. So let's say I am looking at the chemical reaction a very tricky reaction. Reactant going to product. All right, whatever it is, whatever you imagine. One thing turning into the other thing. As time elapses, as I go from time 0 over here to time infinity. Actually, it's just like they were talking about. If I start off with 100 grams of reactant at time 0, how much reactant should I have theoretically by the time I get to time infinity? None, right? I should have. If everything's going right, I should use it all up. Which direction should that curve go then? Down or up? Down, right? And it's going to be kind of curvy. It's going to be a little bit like this. So that's going to be my R, my reactant. So my reactant concentration is going to decrease over time. All right, let's think about then the other half of the reaction. What's happening to the concentration of products? How many products should I have when I start the reaction? 0, right? I just started, there shouldn't be any. How much should there be at the end? A lot. In theory, if this is 1-to-1, as much as reactant, right? If all the reactants turn to all products, it should be similar in the opposite direction. Right, so as my time has elapsed, I've used up all my reactant and I've made all this product. In this class, what we're going to be looking at is specific points in time right? At certain points along the route, how much are there of each? And how long did it take me to get there? So either we're going to look at questions where I wait 100 seconds, what are the concentrations of each? Or we could ask the opposite question. How long did it take to get to the point where I've used up half of my reactant? Right, so if I know up here I had 100 grams, how long did it take me to get to 50? Right, those are two separate questions, but very related. Either you want to know how much concentration is left, or you want to know something about the time elapsed. Yeah. There's no reason why we can't. Yeah. I'd have to give you more information to tell you exactly where that is, but yeah, we can totally look at that. All right, so this is kind of overwhelming. So let me do some stuff first, and then we'll look at the crazy graph. It's the same Roman numeral or letter, average rate versus instantaneous rate. All right, so there's two different ways we could talk about a rate change. Average rate is what we just looked at, right? How much X changes over whatever time, right? You're looking at two spots on the graph and figuring out what the change, the relative change is to those. If I talk about instantaneous rate, want to know, if I look for one spot on the graph, what is the rate at that one spot? Right? This is the rate over the whole graph. This is the rate at one spot on the line. So if I went 10 minutes and stopped the reaction, looked at the reaction, what would be the slope at that 1 second in time? Or at one concentration, what was the slope? So if we look at, this crazy graph, there's a lot of information on here. Right, it's the exact same kind of curve we just looked at. If it's downward sloping, am I looking at the reactant or the product? Right, I'm looking at, in this case, a reactant disappearing over time. We can look at the average rate. I'm going to look over a long period of time, 15 minutes or so, right? A big span of time. And so you would look at, right, 2 x's and 2 y's. So they're looking at the change in concentration, which is here on the y, and how long that took, 15 minutes. So a big span of time tells you an average rate over a long period of time. Instantaneous rate is where we're going to look at one point on the curve. And so the instantaneous rate, I want to know about 0.34 molar, which is right here. But you can't really take the slope of a point, right? There's some mathematical tricks you could do. But in general, you're going to look really close on both sides of that point to figure out the slope. You kind of do a tangent line, figure out what the one point is at that, what the slope is at one point. So in this case, the textbook chose 0.1 molar above and 0.1 molar below, and figured out how big of a time has elapsed between this spot and that spot. And you notice these numbers are different, right? So an instantaneous rate is not an average rate. An average rate is over a long period of time. Instantaneous is over a very short period of time. You're trying to get information about a very small window. Questions on that? Those are mostly just definitions. Alright. In that case, let's talk about how do we write mathematical relationships for chemical equations. Alright, before we even do the actual one, let's do this other example first. Alright, doing my imaginary R going to P reaction. When I had this graph over here, right, what's happening to the concentration of P over time? It's increasing, right? So what should the slope be, a positive number or a negative number? Positive. And so I'm looking at the change in P over the change in time. So its rate would be, right, change in P over change in T. That would give me a positive number, which would be a positive slope. What if I want to talk about the concentration change of R? What has happened to the concentration of R over time? It has decreased, right? What do I know about the relationship between R and P? They're inversely proportional, right? Or equal but opposite. So we're going to describe it that way. That the rate of P being made is the negative of R being made. Which makes sense when we talk about slopes, right? This number should be a positive slope. And by putting a negative sign in there, this is now a negative slope. Well, it's a negative slope. Right, because change in R over time is going to be negative. Just a negative, negative. Just positive. That's because these reaction rates, these right here, are always positive numbers. So you have to have negative in front of the slope to make it a positive number again. Alright, good. So then, let's try an actual chemical equation. Alright, so here I have nitrogen dioxide producing nitric oxide and oxygen gas. So first question is, what is the rate of appearance of oxygen gas using this terminology? Is it going to be more like P or more like R? Is oxygen the product or the reactant? The product, right? So I should say rate is a positive value, right? Because the product, so it should be appearing. Alright, so then let me ask about stoichiometry, then we'll come back to some other things. So the question is, what is the stoichiometry? I'm missing some letters in there. Maybe some C's and some H's. Maybe another O. Something like that. Stoichiometry. That's still not right. But you know what I'm getting at. Close enough. I got the first 4 letters down, and definitely the last 5. The middle. The middle's a little iffy. Alright, so what's the stoichiometry of the equation? How many moles of nitrogen dioxide go in? Right, so we have 2 moles NO2. How many moles of nitrogen oxide come out? Okay, 2 again. And then how many moles of oxygen are produced? 1, right? Hopefully those are all gimmies. Alright, so if the rate of the oxygen produced is change in oxygen over change in time, for every 1 oxygen, if I'm only producing 1 of these, this is where it's going to be conceptually, you're going to not believe me. That's true. So if I make a rate of moles of oxygen, it must be that the rate of nitrogen monoxide is half as fast. It is a half as fast because in order to make 2, I need to go faster, right? This is going to take some thinking on your part. We'll do some numbers here in a little bit. Maybe that'll help. So if I make 1 mole of this, at the same time, I'm only going to make half a mole of that. In the same block of time. Which means if I'm looking at the rate as NO2, it's both half as fast and negative because it's a reactant. So, maybe if I do some numbers, maybe that'll help. so let's say I'm making it right, based on stoichiometry. I make 2 moles of nitrogen monoxide for every 1 mole of oxygen gas. Alright, so 2-to-1 ratio. So I want to make 100 moles of oxygen per second. How many moles of nitrogen monoxide must be made to keep the stoichiometry the same? To make 200. For these two numbers to be equal, what do I have to do to the concentration of NO? If I want them both to be 100 per second, I have to divide number of moles by half, right? Because I just said up here that these are going to be equal. Right, they have to be equal. So for these to be equal, I have to slow down this one by half to make it equal. Just like I had up here. I'll write. Right, just like up here. They'll be equal down here, where it's rate equals delta O2 over delta T equals 1/2 delta NO over delta T equals negative 1/2 delta NO2 over delta T. Right, so up here I had as the products get made, the reactants disappear. Equal and opposite signs. Must be true if I'm doing a bigger reaction. So if the oxygen is being made, in order for it to be equal, I have to slow down the nitrogen monoxide by half to get the same 100 per second. And this one also has to be slowed down, and the opposite sign. Yeah? So just more thinking. It'll come together. Alright, what about my more generic equation? So here's my generic form of the reaction, right? So I just had let's say that's my reaction. I want to use this general form to figure out the overall rate of this reaction. Using the same thing, right? C goes with this. And let's say we'll call this little a, little c. I don't have a b. What should the fraction be for the carbon dioxide? Right, 1/2 delta CO2 over delta T. What should the fraction be for the oxygen? Just 1, right? No fraction, just 1. Sometimes it's easier if you put the, even though it's 1, just to make sure you've done all the other fractions correctly. Alright, what about the C2O5? What does it need? A negative 1/2. That's the only way they're all going to be equal. So you have to, because I'm making double of the carbon dioxide, for it to be equal, I have to half its speed, or to use the equal sign. Alright. Let's do a few more. So here are 2 more equations. Why don't you take a minute or two? This will probably be the last thing we do today. Go ahead and take a minute or two and write the statements like we just did, rate equals, and figure out what fractions you need in order to make these statements of rate equal to each other. Alright, we'll out of the habit, we'll do oxygen first. So what should be the fraction that goes with the oxygen rate? 1/3. Then what fraction goes with my ozone? -1/2. Sure. So if we back up and we... Oh. You're overthinking it. Yep. Just you take the whatever's in front of it and just do 1/3. That's all you do. We're not ready for anything more than that. I'm going to say that to Friday when we do more. For now, it's legitimately just make that into a fraction. That's it. Make it into a fraction. One on top of whatever it is. That's it. Yeah. Yeah. So just turn into a fraction. It was 3, now it's 1/3. It was 2, but it's a reactant, so it's -1/2. I'm not trying to make any of them equal 1. We certainly could. It's a lot of work. No need. No need. So 1/3 to -1/2. So what if I did this one? Right? What's the fraction that goes with this? 1/2. And then this is 1. And then what goes with this one? -1/2. Friday, we will do some math to prove that this is true. Until then, you'll just have to believe me. Friday, we'll do a group quiz also. They'll cover through what we just did. Mastering due tonight. So.